Welcome, everybody, to our lesson on buoyancy. Today, we'll be looking at the forces exerted by a fluid on an object within that fluid. The Greek philosopher Archimedes noticed that when an object was immersed in a fluid, the object felt lighter than its actual weight. I suggest you do this lab immediately. Specifically, the object feels lighter by an amount equal to the weight of the fluid that it displaces. The more of a cookie that you dunk in milk, the lighter the cookie feels. Now, supposedly that thought came to Archimedes while he was in a bath, just inspired, and all of a sudden the idea came to him. It's not a true story, but it is as deeply held a belief as that of Newton and his apple. We like thinking that the flash of inspiration just comes to someone out of nowhere, but I think a lot of you have noticed that more likely it was a result of the fact that Archimedes had been studying natural philosophy for a long time and doing research on the ideas of buoyancy. So if you're counting on a flash of inspiration, probably, do a few years of hard work first. Archimedes said that any body wholly or partially immersed in a fluid experiences an upthrust equal to, but opposite in sense, to the weight of the fluid displaced. Of course, we just say that buoyant force equals the weight of the fluid that's displaced. Let me do a quick derivation for you. That means, put your pens down for a sec, you know who you are. Here's how we derive the idea of buoyant force. Now, on the right, you see a beaker of water, and into that beaker, we can drop an object. And just hold time for just a sec. As that object is fully submerged, but not on the bottom of the beaker, it's just in the middle. It's falling, but we've frozen time as it falls. At that moment, when the object is fully submerged, the surrounding fluid exerts forces on the top and bottom of the object, and the sides, but we're going to ignore the side forces for now. There is a force on the top pushing down, and a force on the bottom pushing up. Now that force is pressure times area. Pressure is rho gh, so either force depends on the density of the fluid, gravity, the depth in the fluid, and the surface area of the top and bottom of the object. Because the bottom of the object is deeper, it will experience a greater upward force than downward force. The bottom of the object is pushed up more than the top of the object is pushed down. The upward force is greater, so the net force exerted by the fluid is upward. We call that upward force the buoyant force. So let's go back to our derivation. I've labeled the depth of the top of the fluid with a D. The top of the object with a D, and the bottom of the object is a distance h lower. So the net buoyant force equals the magnitude of the force pushing up against the bottom of the object minus the force pushing down against the top of the object. So the depth of the object at the bottom is d plus h. So rho gh would be rho g d plus h. Force is pressure times area, so rho gh times area. But notice, because h is the height of the object and area is the surface area of the top of the object, h times a is just the volume of the object. So what that means is that the buoyant force acting on this object that is fully submerged is the density of the fluid times the volume of the object that is submerged times g. And density of the fluid times the volume that's displaced is just the mass of the fluid, which means that the buoyant force is equal to the weight of the displaced water. So Archimedes says buoyant force is equal to the weight of the displaced water, the mass of the displaced water, times g. Which means that buoyant force is the density of the fluid times the volume that is the object submerged in the fluid, or the amount of the object that's submerged in the fluid, times g. Now, I'm pretty careful about the subscript on the volume there. It says V submerged. If only part of the object is submerged, then it wouldn't be the whole volume of the object. So let's try it out. A 100 gram object submerged in water displaces 15 cubic centimeters of water. What would it seem like that object weighs? For this, we need to know one useful thing about water, and that is its density. The density of water is very conveniently 1 gram per cubic centimeter. So 15 cubic centimeters of water make the apparent mass change by 15 grams. If we were just holding a 100 gram cookie in air, it would feel like it has a mass of 100 grams. If we dunk that cookie in something with the density of water, it would feel lighter. So it would feel lighter, in this example, by a mass of 15 grams. It would apparently have a mass of 85 grams, which would mean that its apparent weight is 0.85 newtons. Or it would mean that the buoyant force is 0.15 newtons. So here is a 200 gram toy. Not great at drawing digital scales. It says 200 on it. That is a 200 gram toy. Its actual mass is 200 grams. But if we get a beaker of water and dunk the toy, a scale might say its mass is only 160 grams. That means that its apparent mass is 160 grams. So in air, the mass is 200 grams. Submerged in water, its apparent mass is only 160 grams. The difference between those, between the actual mass and the apparent mass, is equal to the mass of the water that the toy displaces when fully submerged. And that means that the toy displaces 40 grams of water. That's 200 grams minus 160 grams. Displacing 40 grams of water means the toy displaces 40 cubic centimeters of water. Even without a measurement of the toy's volume, we know its volume by the change in apparent mass when the object is submerged. Its mass changes by 40 grams. So we know it displaces 40 grams of fluid. Because we know the density of water, that gives us a clue about its volume. Well, density is mass divided by volume. The mass of the object is 200 grams. The volume of the object is 40 cubic centimeters, so we can find the density of an object just by comparing its mass in air to its mass when submerged in a known fluid. In the lab that you'll be doing today, you're going to submerge objects of known mass and known volume in a fluid of unknown density. You'll be using the same process, but in the lab, you won't know the density of the fluid, just like in this example, you didn't know the density of the object. Good luck, everybody.